And let's see, what I'd like to do is let's go ahead and bring in some sources. So what it is that I happen to have here is when I click on this tool here, I end up with this dialog box. And in this dialog box, I'm going to go to power sources. And on power sources, I want an AC power source. So I click OK, and I will place an AC power source, let's say there. And then I can close this guy. I would like to actually want to bring in a ground. So right here, I'm going to bring in a ground. Hit OK. So somewhere here, I will plant a ground. I'm done with this. Now I'm going to go to components. And on components, this will be basic. And basic, I want a resistor. So I'm just going to, oops, what is this? Cancel. I just want a resistor. Hello. Resistor. Okay. And place a resistor. Kaboom. I have a resistor. And now I will select a capacitor, and I will place a capacitor. All right, this is plenty. Now, what I'd like to do is to confirm something here. Let me go off screen for just a moment. All right, so let's go here and time constants. Okay, so let's go to here, and let's go here, and let's take a look at, see if this is what I'm looking for. Okay, this would work. All right, cool. So I'm going to grab this guy, move this here, grab this guy, move this up here, put this guy here, and let me increase our view. So view, zoom in, and view, zoom in. Okay, pretty good zoom. And now I'm going to change some values. I don't need the rest of the screen to be quite so large, but I want to see some of the values that are on here. So I have a number 472. That's great. So my capacitor is going to be a number 472. What do you remember about deciphering the code for a 472? How do you decipher the code for a 472? We did this before.
You do a 4, then you take the 7, and then you put 2 zeros.
And that's a good start, right? So a number 472 cap. The task was you take a 4 and the 7, and the 2 indicates number of zeros. That part is correct. But there was something else we had to add at the end. What was the something else we had to add at the end? Because that's not the capacitor value yet. What specific thing do we have to add back here?
Picofarad.
Okay, it is always going to be in picofarads. Everybody say picofarads. You need to speak it. Picofarads.
Picofarads.
And how many, what is the power of 10 for pico?
-12.
So this will be 4700 times 10 to the -12 farads. You need to enter this into your calculator. When you enter this into your calculator, this will tell you how many farads we are going to have. So 470, let me clear.
4.7.
Not quite. 4.7 thing. It's not just 4.7. I need something there. Tell me what I need.
Nano.
Nano what?
Farads.
Ah, okay. So when you key this into your calculator, and I have it keyed in my calculator, 4,700 exponent negative 12, the moment I hit enter, because my calculator is set up in engineering mode, this will give me the engineering equivalent. So it is 4.7 E negative 9, which means 4.7 nanofarads. Are we clear how to decipher this capacitor code? So we've done this once before. That's a reminder on what we need to do. So we need to be able to decipher capacitor codes for this exercise, and this was a good reminder on how to do things. So the key thing was, yes, you started off this correct. It was a 4 and a 7, followed by the number of zeros, which was 2 zeros. And then you have to add picofarads. And you have to remember pico is a negative 10, excuse me, 10 to the negative 12. You punch this into your calculator, and if your calculator set up in engineering mode, you will have 4.7 nanofarads. All right, so that being said, let's go back to our share and come on, mouse, share here and share. Cool. I'll move this out of our way. All right, so I'm going to double click this guy. Give it a moment. And where the capacitor value comes up, it shows a 1 micro. I'm going to take that out and type in 4.7 N. Oops, not caps, lowercase, and then hit OK. So now I have 4.7 nanofarads. Are we good with that so far? Cool. Then we have to change our source here, and our source is going to be an AC voltage source, except I'm looking for, instead of 120 volts RMS, I am looking for a peak-to-peak value, and let's take a look here. It shows it to me in RMS. Okay, so I'm going to want this. 10 volt peak is going to be a 7.7 volts RMS. So we're going to type in 7.07 and then click OK. And I'm going to select this guy, and I'm going to do a Control R, which rotates it in this direction, like so. And I'm going to look for a value for this resistor. And let's see, I think I've been given the resistor value. Let's see, I should have it here. Function generator, output. Do I have a resistor value? Let's see, in this exercise. R1. Okay, I left that out specifically. Okay, we have a formula that is on here. This is a new formula, this X sub C formula. X sub C is how this capacitor will behave in the presence of the AC. So it allows us to take the capacitor value and work out a ohms of what this guy will represent with respect to AC. So way back at the beginning of our semester, going way back to the beginning of our semester, you were given this document. And let's find electrical. I'm looking for electrical. electrical units. No, not practice. I just want electrical units. Where are my electrical units? Week 1, WK1. Oh, here. Helps if I'm looking in our class. 50. And here. Okay. And let's go here. And I said to put this in the front of your notebooks, electrical units table. Because now we're getting to the point where we're actually looking at a number of these items. We started off, everybody can see my electrical units table. So my electrical units table, we started off reviewing what is voltage all the way through power. Those are the basic ones we started off with, which is VIRP. Then there's a discussion here. What is conductance? What is charge? We got into a discussion a couple of weeks ago regarding capacitance. And the capacitance over here was defined as being one of many things. It was defined as being the ability to store charge. So let me reduce the size here. Bring this guy over and magnify this just a touch. Okay. The ability to store charge between conductive plates is the characteristic known as capacitance, measured in units of farads, and the symbol for farads is capital F. Inductance is represented by the letter L, which you saw earlier. Units are in henries, and Henry's symbol is a capital H. What is this? The ability to pose a change in current, which was the definition in one of the definitions I've given you. And in the other definitions, the ability to create a magnetic field as current flows through a circuit or a wire. We talked a little bit about frequency before. Frequency is a lowercase f and measured in units called hertz, and the symbol is capital H, lowercase z. What does hertz mean? Number of cycles per second. So you want to make sure that wherever you have this in your binder or in your notes, you bring this back forward. And if this part of this table is not in your notes, you want to transfer this into your notebook, into your composition book for future reference, because it helps to keep track of some of the new words that we're going to be introduced to. And some of the new words we're going to be introduced to today, reactance, not resistance, it is called what? Reactance. And reactance is measured in units of ohms with the symbol omega, just like resistance. However, it's not resistance, and we don't use the letter R here. What letter do we use? We use the letter X. So X for reactance, measured in units, measured in ohms. What is it? It is defined as the opposition to AC by either a capacitor or an inductor, and it's typically called inductive reactance or capacitive reactance. Who gave this to us? Mr. George Ohm. And so the key words here, the very first words here are opposition to current. Does that sound like resistance? Isn't resistance opposition to current? The answer is yes. Well, we have other kinds of opposition to current. Other than a resistor, a coil will represent opposition to resistance, and so will a capacitor. But it will do so specifically in the presence of AC. So for a capacitor, it has a very specific name. A capacitor is called capacitive reactance, and a coil demonstrates inductive reactance. So X sub C, we pronounce this as X sub, like subway, or subscript. X sub C represents capacitive reactance measured in units of ohms with the omega. And this is specifically defined as opposition to AC current by a what type of device? By a capacitor. And then if we look a little further down, you will be able to see X sub L. And X sub L is the symbol that represents inductive reactance. Inductive reactance is in ohms using the omega, and its definition is given as opposition to AC current by an inductor. Okay? So we only see these terms, in the presence of what? AC. These quantities do not exist in DC. Then we have one more word, new word down here. This new word is impedance. And impedance is given the symbol Z, and it's also measured in ohms using the omega symbol. And what does this represent? It represents the total opposition to AC current in a circuit that has a resistor with a cap or a coil or all three connected. If you look at this schematic that I have, nudge this slightly this way. If you look at the schematic that I have over here, do I have an AC source? Do I have a capacitor? Do I have a resistor? I'm going to connect these in a moment. And so the capacitor, this guy, is measured in what units? Nanofarads. We interpreted that based on the code that we were given, 472. In the presence of AC, it will exhibit a certain amount of ohms, which we can measure, which we can calculate, and then determine the effect of very, very quickly. So we're going to need frequency in here, and frequency is measured in what units? Hertz, capital H, capital Z, and what does frequency mean? Number of cycles per second. And it turns out in your wall outlets in the United States, that number of cycles per second is 60 hertz. In other countries, it's 50 hertz. But through many parts of the world, it does happen to be 60 cycles per second. We're going to need a very specific frequency for this exercise, and this exercise is given as 2.75 kilohertz. So I'm going to come to this voltage source, I'm going to select it, and I'm going to leave the RMS as 7.07, but I'm going to change this to 2.75 with a K. And I need to do that as a 2.75 and hit OK. So now, does my frequency jive with this exercise? 2.750 kilohertz, 2.750 kilohertz. Very good. All right. Now, as another review, if you recall, let me diverge from this for a moment. We have RMS here, but my exercise is calling for 20 volts peak to peak. What was the relationship between these guys? And are we talking the same thing? Are we talking something different? If you recall, let me stop the share for a moment, and let me come back to the camera screen. And on the screen, let me move this guy out of the way. So on the camera screen, if you recall, we have an AC waveform, like so. And we have on that AC waveform a positive V peak, and we have on the AC waveform a negative V peak, and we have on the AC waveform we calculated from here down to here a volts peak to peak, and then there were two additional quantities that we brought in, and one of those additional quantities is right about here, and it's called VRMS. Remember that? And we had a very simple relationship between these quantities, which was this. My VRMS on the top of the circle, V peak over here, and over here I put down square root of 0.5. That's approximately the same as this circle, VRMS V peak, and this is 0.707. So on your calculators right now, just to remind yourselves, because we had this discussion well over a month ago, take square root of 0.5 and hit equals on your calculator and show me what you get. So square root of 0.5 is what I'm needing you to calculate, and I need to see your calculators on the screen right now. Good, Christian. I see that. Andrew and Kyle. I see that for Andrew. Kyle is coming up. That's good. And then Pauline and Wenbin. You can show me that. Yeah, that looks good. Thank you, Pauline. Wenbin, I need to see your calculator. If you punch in square root of 0.5. Yeah, punch in square root of 0.5, hit equals, and what does your calculator show you? It should show you this number here. On my calculator, it works out to be 707.106 milli, which is basically in decimal form, 0.707, okay? So the square root of 0.5 is roughly 0.707. So if we have a 20 volt, if 20 volt peak to peak, that means from the top all the way to the bottom is 20 volt peak to peak. If that's what we're given, comma, then V peak is equal to blank. If the whole thing from here to here is 20 volts peak to peak, what is my V peak going to be? Question goes to Rolando. What is V peak going to be? The whole thing is 20 volts peak to peak from the top to the bottom. What is half of it going to be? Because V peak is 1/2 of the peak to peak.
Be 10 volts.
I'm looking for the rest of your answer, my friend. Somebody want to chime in? Pauline, you want to chime in?
It would be 10 volts peak.
That's the proper full verbal output I was looking for. It's not just 10, it's not just 10 volts, it's specifically 10 volts peak. A 20 volt peak to peak, half of that is a volt peak, and it must be read and spoken as 10 volts peak. Now, if I have 10 volts peak, then the next question is going to be, then my VRMS is equal to blank. This question would go to Mr. Cortez. Mr. Cortez?
7.07 volts RMS.
Okay, so you end up with 7.07 volts RMS. Okay, so was this exercise, I know it's been over a month since we looked at this stuff, but was this exercise here?
How did we get 7.07?
By using this formula here. If I'm looking for VRMS, it is nothing more than taking the V peak and multiplying it by square root of 0.5, which would be the same, very close to being the same as V peak times 0.707. So these circles are what gives you the conversion from RMS, from peak, from the V peak to RMS. Okay?
Okay, I understand now. Thank you.
Okay, sure, you're welcome. Yeah, as questions come up, don't hesitate to ask. And at the moment that the question is raised is when you have to ask the question. So I appreciate the question. So yeah, as I've said, it's been several weeks since we last looked at this, and I bring this back to light because the exercise that we're given is given in volts peak to peak. And I'll go back to our share screen, hit share. Good, and in the share screen, our directives were given as 20 volts peak to peak at 2.75 kilohertz. So the MultiSIM asks for the value in RMS. So I punch in 7.07 volts RMS, which is the same as 10 volt peak, which is the same as 20 volts peak to peak. So this voltage source on this paper is the same as this voltage source in MultiSIM at this moment. The frequency is the same and the amplitude is the same. The only difference is the format of voltage here is expressed in RMS and the format of the voltage here is expressed in peak to peak. Why is there a difference? Because Co wants you to think. The Co guy wants you to interpret what is a 472? And you actually remembered how to convert the code of 472 into a capacitance value, worked out to be 4.7 nanofarads. The code guy wants you to think. You have 20 volts peak to peak. Oh, but you have to express in RMS format. Wow, how do I do that? You take the 20 volts peak to peak, divide it in half, you end up with 10 volt peak. You take the 10 volt peak, plug it into the formula to get RMS, you end up with 7.07 volts RMS. So far, does everybody understand what we're doing from here to bring it into MultiSIM? So far, so good? Okay, now I'm going to connect these wires. So I'm going to go here and connect that wire. I'm going to go here, connect that wire. I'm going to go here and connect this wire. And I'm going to go here and complete the circuit and connect that wire. I'm going to nudge these, make sure the wire follows. That means I have a good connection. I'm going to nudge this guy up. Yes, the wire follows. That means I have a good electrical connection. Nudge my source. Yes, my source follows. I have a good connection. So far, so good. Now, the next task is to learn this formula here, X sub C is equal to 2 pi FC. This is the formula that allows you to calculate the number of ohms. Well, what is X sub C? In review, X sub C is called what? Everybody read it out loud to yourselves. Capacitive reactance. Say it again. Capacitive reactance. And we read this as X sub C. And so, yeah, that's right. And it's measured in what units? Ohms. And it is defined as opposition to AC current by a capacitor. Notice in my MultiSIM, I only have a capacitor value. I don't have ohms up here. There are no ohms. So I need to pop in ohms up here. Well, I won't pop in, but I need to calculate this. And so what I'm going to need to do is to pop it into my calculator. So I'll show you how easy that is to do. We come back to the formula on this paper, and I will go to stop the share screen. And now let's take a look at writing this down. So this is called capacitive reactance. And the capacitive reactance formula is given, let's give you all the pieces. So this is equal to X sub C, and this is defined specifically as equal to the opposition to current to AC current by a capacitor. There will be no X sub C in DC circuits. This X sub C only exists for AC circuits. And so you're given this formula, X sub C is equal to 1 over 2 pi F and the value of C. In our example, this would be equal to 1 over 2 times pi times 2.75 kilohertz times 4.7 nanofarads. So that is the formula written out. On your calculator, what you're going to do is your keystroke sequence. And as I've stated before, I'm going to use the keystroke sequence that is most uniform for the majority model calculator we've designated for our class. So your calculator, if it is not our designated calculator, may have a slightly different sequence. You'll have to find your own way for change sign versus negative. Pi might be a second function. So I'm going to write it out this way. This will become, keystroke sequence will become 2 times pi times, and for some of you, that pi might be a second function in order to get to your pi key. That's possible. And then 2.75, and then exp. And for some of you, that exp could be a 10 power x key. You'll have to find which one is yours, power 3. And then we're going to multiply this by 4.7. And the nano, again, you're going to have an exponent. And here you're going to have a change sign. And for some of you, that change sign could be a +/x, or it simply could be a key, a minus sign in between parentheses. And nano, if you recall, was power -9. Then you hit equals. That only calculates the denominator. You still have to reciprocate it, divide it back into 1. So we will use the reciprocal key here, x -1, and then hit equals at the end. So that is your complete basic keystroke sequence for finding x of c. So I'd like each of you to do that. And I will go ahead and do the same on my calculator. And so 2 times, and for mine, I have to hit second pi. So there's my pi, and then times 2.75, and I have to hit second double E, 3, and then times 4.7, second double E, -9. So what I've done is I've keyed in the denominator. I'm going to hit equals. After the first time I hit equals, then what do I have to do? I have to hit reciprocal one more time, and I have to hit equals one more time. So here's my reciprocal key, and here's my equals. And what is it that you calculate? Show me what it is you calculate on your calculators following this keystroke sequence. So, Mr. Cortez, what is it that you calculate?
12.31 kilo. Then
Remember, this is opposition to current, so it must be in units of, just like resistance.
Kilo ohms.
Ohm. Okay. And Pauline, what do you have?
Strange. I actually came up with 27.35 kilo ohms, but I guess that's wrong.
Review your calculation. These steps, I think I wrote them down correctly. 2 times pi
Right.
times the 2.75 kilo times the 4.7 exponent -9, hit equals, and then hit reciprocal, because it should automatically reciprocal your last answer, hit equals again.
You know what? I think I forgot to reciprocal, and that I think that's why I'm getting 27. So if you have that, yeah, thanks.
Okay, and let's take a look. Wenbin, do you have a calculation for me, my friend? Wenbin, please speak to me. So my question was, in following the sequence that we just last did, do you have a calculation for me? Yes or no? Is your mic not working, Wenbin?
On. And I got answer.
Okay, Rolando, your calculator needs to be in engineering mode. And so Wenbin, Yeah, following this keystroke sequence, I need you to understand and feel confident that you can give a correct answer. And Rolando, do you have, okay, there, now I see it more clearly. Andrew and Kyle? All right. So everybody's showing the correct answer, which on the calculator shows up to be 12.31 with a K, because it's power of 10, 10 power 3 kilo ohms. Keep in mind that your X of C is in units of ohms, okay? Now, that having been said, we now have the value of capacitance reactance in this value, and I can now pop in a value that I will choose for my share screen. So before I do, does everybody feel confident in using this formula and making a calculation? Let's do a practice. Let's just practice one more, okay? So for practice, F will be equal to 15 kilohertz, and C will be equal to a 175. And based on this, I am looking for, this is the number 175. So based on this, I am looking for a value of C. Based on this, and the formula, X of C is equal to 1 over 2 pi FC. I will be looking for an X sub C. So let's go ahead and practice this. Give me a new frequency and a new coded value for your capacitor. You have to decipher that capacitor code, write down the value of capacitance that you're going to be using in this formula, and then pop in the frequency into this formula and then calculate an X sub C. So let's go ahead and work on this. So walk me through these steps. Kyle, you're up. So Kyle, if I have a 175, how do I start my deciphering of a 175? Walk me through this.
So you take the 1 and the 7, and then you add 5 zeros
Okay, 1, 2,
to the
3,
pico, and it's picofarads.
and picofarads, good. Is everybody okay with this part of the interpretation process? Kyle says you start off with the first 2 digits, then you add in the number of zeros, which is specified by the 3rd digit, says 5, so I have to add in 5 zeros, 1, 2, 3, 4, 5, and we must write down picofarads. So this is our starting point in the decoding process. What do I do with this information in the decoding process now? And the question goes to Andrew. What do I do now?
You want to take that over and put it into narrow farads? You
Well,
want to,
is it always going to be in nanofarads? We need to find out. So what do I need to do with this to determine what this value is going to be? Because it's not always going to be in nanofarads.
you got to times it by 10 with the negative 12.
Okay, and we're going to put this into our calculator, yes?
Yes.
So when you go ahead and do that, what is your calculated value for capacitance?
Let's see. Uh, 1.7 to the negative 6, or is it 7?
Yeah, and so what engineering prefix is that?
That is
Engineering -6.
micro.
All right. So how many people agree we end up with a 1.7 engineering -6? So we would write down a 1.7 micro followed by farad. Is everybody okay with that interpretation and that process? So far, so good? Now we want to take this information and calculate X sub C. So what is my keystroke sequence to get to X sub C? So we write out our denominator. So it will be 2 times pi times, in this case, the frequency is given as 15 exponent 3. And then we roll times again. And now our capacitor value, which is 1.7 exponent, this will be change sign. And we saw in our calculator, it was change sign to the power of -6. So we have a -6. We hit equals. And after we hit equals, we follow that with a reciprocal key and follow that with an equals one more time. So based on that, now I'm looking for a calculated value for x sub c. So let's go ahead and take a moment to do that. 2 times second pi times 15 3 times 1.7 exponent -6. And then equals, and then reciprocal, and I'm about ready to hit equals. So I'm looking for a calculation, and Pauline, might you have this calculation for us, please?
It's a bit tough, but I think I've got 13.86. No, I'm not getting it right. When I hit equals after the reciprocal, it doesn't quite equal.
Oh, okay. Well, here again, it depends on your calculator. But here, let me offer a big suggestion for you, and this will work this way. Check this out. At the very beginning of the exercise, start with an open parentheses, and then at the end of this sequence, let me think. All of this.
I think that's why I'm getting it, or I'm not getting it correctly.
No, here, because it varies depending upon the calculator. So what you can do is this. You start your calculator with a 1, divide by open parentheses, all of this, close parentheses, and then equals. Then there's no more reciprocal at the end. That may work better for your calculator, okay? So try this. 1 divide by open parentheses, and then the sequence that we had, don't forget the close parentheses, hit equals, and then you don't have to do any reciprocal or after that. Try that sequence.
Let me try that and I'll give you the answer.
Okay, and then let's see, Andrew, let me see what you got. And so how many ohms? Okay, there's no engineering after that. That's just 0, 0 engineering, right? So you end up with 6. Looks like there, looks like there, looks like there. And I see Rolando's. Rolando, how'd you end up with such a big number? That's interesting. Yeah, you have to, Rolando, you have to hit reciprocal one more time. Christian, your final answer? Just read it out, please.
6.24 ohms.
6.24 ohms. This would be equal to your X sub C, okay? And so Rolando, you were one step away from that, because what you did was, if you look at my calculator, you did this part. You did the 2 times pi times 15 exponent of 3 times 1.7 exponent -6. You hit equals and you end up with 160 milli. Remember, that's only the denominator. You have to reciprocate that answer one more time, and then you'll end up with this number consistent with everybody else, which is 6.24 ohms. So Rolando, could you double check that calculation, please? And Pauline, did that new sequence work better for you?
I'm still struggling with the calculation. Hold on.
Okay. And if that persists, what we can do is, after our lecture today, we can go offline for just a couple of minutes and watch you through the calculation steps and make sure you feel comfortable with it. Hey, Rolando, you got it. Hey, good job, amigo. Very nice. All right, you're spot on. Wenbin, are you okay with this calculation, pal?
Yeah, be fine.
Can you show us calculator? Do you have any kind of camera on there on your system? I can't see your
What do you
face
mean?
or
I
your
cancel.
no can't. All right, but I want to make sure you're comfortable with this calculation. Okay, so we end up with 6.24 ohms. All right, so that was a good exercise in capacitive reactance. What is it? It is opposition to AC current by a capacitor. Frequency indicates we have AC. And in the example that we were given, the first example, we popped in the numbers 2.75 kilohertz, 4.7 nanofarads. We calculated this. For practice, new frequency, new coded value. You were able to decipher the coded value as 17 followed by 5 zeros. Picofarad, when you punch this into your calculator, you should be able to interpret the 1.7 microfarads as being the cap value. Then you needed to pop all of those numbers into the formula. And there's a couple ways of doing this. I explained this already. A couple ways, depends on your calculator. But the sequence in black without the red, if you follow the sequence in black, as most of you have, you should end up with 6.24 ohms. And then an alternative method is with a different style calculator, 1 divided by open parentheses, everything here, parentheses, equals, and that will give you the same. You don't have to hit reciprocal and equals at the end of that sequence in red. Still should be able to get this. All right, so that's good for practice. Now let's go ahead and assign a value. Let's go ahead and assign a value. So let me go back to the share screen for a moment. Go back to my share screen. Okay. And so on my share screen, this exercise was a practice lab final. And so as practice, I left out the R value intentionally because as a practice, when we're doing this face-to-face, one student might get a 2 kilo ohm, another student might get 3 kilo ohms, another student might get 4 kilo ohms. And that way I can see by different results that they are calculating their work individually and not sharing their work. So that's why you don't see ohms listed in this particular example. But for ours, we will pop in a specific value, and I don't choose to use 1K. So since we had 12.31 K for the calculated X sub C, I'm going to pop in 6K equals 6K ohms. All right. So this exercise will have 6 kilo ohms. So now what we have is an opportunity to see something very interesting that will give us this demonstration of two different waveforms. And we should be able to see something known as phase shift. This is the practical visual output of how a filter can work. And so if I go to make the connections on my MultiSIM, I'm going to go to my MultiSIM, and we've built the circuit in MultiSIM. I'm going to come over here and look for, there's a multimeter here, function generator. Can you see the little, I'm on the far right-hand margin of MultiSIM screen. Can you see the little pop-outs, the little tags, the labels? Can you see multimeter on your screen? And can you see function generator? Can you see the next one, watt meter? Can you see the next one on my screen says oscope? Click and drag, or double click. And one should pop in here. Here's an oscope, cool. So there's an oscope. And I have two channels on this oscope. And so what I'm gonna do is I'm gonna bring in two more grounds. Okay, so here's a ground. And here's another ground. Close this off. And so for my negative side of the oscope connections, I will have a connection to ground and I will have a connection to ground. All right. What I'm going to do, if you follow this drawing, channel 1 has to connect all the way to the top of my source. Channel B has to connect to the top of the resistor. So I'm going to connect here, down, over, click here, come all the way over to here, click, and then come down and click. Now do I have from channel A, positive side of channel A of the oscope, a wire that goes all the way to the top of my voltage source. And that mimics this wire connection in my lab to there. Channel B is going to come from the positive side of channel B oscope around here to the top of the resistor. So let me go ahead and view again. Let me zoom in again. And let me zoom one more time since I have all kinds of space to do this with. This is nice. Zoom in. All right. I click on channel B wire, click, bring it over to here, click, come up to here, follow the grid lines, click, and come over, make a connection here and click. Great. Now do I have connections that mimic what are shown here? Channel A positive goes to the top of my source. Here's my channel A positive goes to the top of my source. Channel B positive comes over here, goes to the top of my resistor. Channel B over here goes to the top of the resistor. Both grounds, the negative side of channel A and the negative side of channel B, are connected to ground, and they are connected to ground. So I could have wrapped wires from here down to here, but that's just more wiring and it's not necessary. Remember, ground over here, the ground over here, and the ground over here are all the same point. I just don't have to make those wire connections. That being said, I am ready to simulate and be able to look at some kind of an output on this. So in MultiSIM, I'm going to click Run and double click this guy, and I have a nice oscope, and I'm going to have to change my timing on this. So on my time base, let's go ahead and change this where I can see these waveforms. There we go, very nicely. And I'm going to do one more. So 100 microseconds, that looks really good. Oops, can I see it there? Let me run it. And let's hit reverse. Okay, we can see it a little better. And, all right, don't want to hit save. Let me see if I can hit a pause, run, pause, run, pause, and that's good. And move this over. Hallelujah. Isn't this nice? Don't I end up with two waveforms and they're not in phase with each other, meaning this waveform doesn't peak at the same time this lower one peaks. The larger waveform crosses at a zero. It crosses from the negative half cycle to the positive half cycle. Its cross point does not match the same cross point for this particular waveform. They are out of phase with each other. And based on reading this oscope very carefully, we should be able to interpret a number of things mathematically and interpret a number of things by measurement. So let's show you how we do that again. I'm going to go ahead and hit stop. Stop on the run. Building the oscope, building the oscope connections, building the circuit, I hope is fairly straightforward. Let me show you again the operation of the oscope so you can see what it is we did in order for us to reveal the waveform. If I double click this right now, well, that was from the previous run. I'm going to hit a run. So now I've got electricity flowing in the circuit and it's working. Now I double click this guy and I see this. Now initially you might not see this. Initially we saw something that looked like this. Initially we saw something that looked like this. You couldn't see waveforms. So if you see a pattern like this, it just means that our time base right here needed to be adjusted so that we can separate all of these waveforms that are so close together into something that is readable, because right now it's not readable. So you come to this part of the O-scope display where it says time base, and we're going to click the down arrow. And notice when I click the down arrow, the peaks are no longer as congested. They're not packed on top of each other. They look like they're starting to get spread out. If I click this down one more time, do I have more separation? If I click this one more time, do I have more separation? And click this one more time, I can start seeing two waveforms, and they're distinctly out of phase with each other, but they're too close together, too many peaks on my display. Click this one more time. They're starting to look better. I still have too many peaks on the display. Click this one more time. That's a good one. I like this particular one. This is currently, my time base is 100 microseconds per division. So I'm going to hit a stop. And then I have a cursor here, a horizontal cursor. I can slide this left and right. So I'll just slide it so I can see the waveform more clearly. And how can I tell which? Well, channel A is set at 5 volts per division. Channel B is set at 5 volts per division. So since they are the same scale, one value, bless you, one value is decidedly larger than the other. So if I look at this, which one of these do you think is my input, my channel A? Which one of these do you think is my output, which is channel B? Look at this and just kind of noodle this out for 10 seconds here. What do you think? Who's got a thought? Who would like, you all have a thought. Who would like to verbalize their thought? That's probably the better question. So here's a clue. You ready for the clue? Okay, code guy gives you a clue. What was our source? 10 volts. 10 volts in what form? RMS. Remember, O-scope doesn't read RMS. O-scope only reads peak, or peak to peak. That's all the O-scope will ever read. So what is 7.07 volts RMS as a peak value? We determined that earlier with a calculation from this diagram. Our diagram said 20 volts peak to peak, yes? What is the volts peak? The peak voltage was 10. Does one of these waveforms shows 10 volts peak?
I think peak to peak will peak to the middle would be what, 3.53?
Peak would be, here's the middle line. And so the middle line we would count up to one of these. And which one of these represents 10 volts peak? The shorter one or the taller one? Which one?
Oh.
Why? Why the taller one?
It's 5 millivolts. I mean, 5 volts per division. No, so it's 2 divisions.
Hey, that's right. Remember, right here's your scale. We've done this some weeks ago. We have a vertical scale that tells you each square is worth 5 volts per division. And if you look at this, here's a square. From the 0 line to here is 1 square. From this square is another square. So if you look at this one right here that my pointer is pointing at, from the 0 line, I have 1 division, 2 divisions. So 2 divisions times 5 will give me what voltage peak right at this point? That will give me 2 times 5 is 10. So isn't the larger waveform a 10 volt peak? Are we good with that? So the larger waveform shows 10 volt peak. The smaller waveform shows whatever voltage we're going to measure across the resistor. Now, if I change my scale for channel 2, here's my scale for channel 2. And channel 2 is now the larger, appears to be the larger waveform. And how many divisions for this peak here from the 0 line to this peak? It's 1, 2, and it looks like maybe 2.2. But that is 2.2 times how many volts per division right here? 2 volts per division for channel 2. So that works out to be 4.4 volts. 2.2 times 2 gives you 4.4 volt peak for channel 2. So if I bring this down to be the same scale, because that's what we want to compare, both of these at the same scale, if this is at 5 volts per division, this is a little more than 4 volt peak. So we approximated 4.4 volts peak. We're going to check all this out with mathematics in a very short period of time. Okay, yeah, Wenbin, if you could put your microphone on mute. Okay, thank you. All right. Any questions at this point, because before we dive into the math?
What?
Who's got a question? Anybody? Okay. So can you, by an assignment, be given a circuit, some peak-to-peak value, some frequency, some coded value for a capacitor? Do you have the confidence to be able to take that coded value and that peak-to-peak value, build this circuit in MultiSIM, shown over here, and put in the appropriate RMS equivalent, put in the coded value in terms of farads, not just coded value, and I will assign a specific value of R in this exercise such that you can build this in MultiSIM, bring in a oscilloscope, wire up the oscilloscope in this fashion, be able to hit play, go, click the oscope in order to get the display, and then adjust the oscope for time base in order for the waveforms to become separated. Make sure that these are both in the same scale. You hit stop, and then adjust your cursor left and right so that the last thing you want is something like this, where you don't fill up your screen with the waveform. Once the oscope, if you have it in the run mode, like this, everything's dancing around. So I'm up here, I'm hitting the red square at the top, red square, follow my pointer, red square. If I hit the red square, it stops the wiggly waveforms. Then you come over here, bring this cursor over so you can see the waveforms, now nicely separated. Adjust your time base to avoid this type of pattern initially. Adjust this so you can see these waveforms nicely separated. And once you have things nicely separated, then you want to bring in your cursors if you can. And right here happens to be your cursors. Notice my mouse pointer, there happens to be 2 little arrowheads at the top and very thin line. So when I bring my mouse pointer, which starts off as an arrow, over here, it changes from an arrowhead into this, which allows me to pull this over. And this has a blue cursor line following it. And if I wanted to, I can put this right at the peaky peak top of this particular one, as close to the peaky peak top as I can get it. And does my display show me I have something very close to volt peak right here for channel A? This tells me, because I'm on here at the very peak, that I have a 10 volt peak. If I bring over here, bring in the other cursor, grab it. Can I grab it? Come on, there we go. Bring this guy in and move this over to here. Looks like the peak of this guy. And for channel B, isn't that very close to what we guesstimated as 4.4 volt peak? Okay, so channel B at 4.4 volt peak, channel A at about 10 volt peak. Now that's how you can also use these cursors to confirm the peak values. More importantly for us, we want to determine something called phase shift. We want to determine the space between when this lower waveform goes to, crosses over, and when this one crosses over right here. So the blue cursor is where the small waveform crosses over from negative half cycle to the zero line to the positive half cycle. And then the red cursor is adjusted to where the large waveform goes from the negative half cycle, hits the zero line to the positive. This space in between is very important to us. This space in between is given to us right here, T2 minus T1, as 63.2 microseconds, 63.197. I can also achieve that difference if I do this. Let me move this cursor over to here. This is where the positive swings over to the negative, and I can move this one over to here. The intersection point is where the positive of the smaller waveform switches from positive half cycle to negative half cycle. That is my 0 point. And if I look at the time distance between these two guys, am I still somewhere around 68 and change microseconds? Okay, so that information will be very important for us in a little bit, because we're going to do the math to do the calculations and see if all of this matches our calculations. So cursors, where do we get them from? We get them from the far margin of our oscilloscope display. I'll move them both back over here. So this is your waveform after you've gotten it stabilized, after you've gotten it filling the screen, after you've gotten it widened or narrowed. This is too wide. This is too narrow. This is good right here. After you ascertain that the voltage is 5 volts, 5 volts, then you bring in the cursors. You come up here, grab one of these lines, right there. Here's one, move that to a point, grab the next one, move that to another point, and the time in between, somewhere between 67 to 68 microseconds, okay? It doesn't matter that it says negative or positive. That's if I move this over to this side, say there, and I move this guy over to this side, say right there, as best as I can nudge it. I'm still getting something very close to 68 microseconds, yes? Okay, okay, and then now there's no negative, only because the red cursor is before the blue cursor. So negative or positive here doesn't make a difference. What is important is this number. Now, what do we need to do mathematically to confirm everything that we've done in MultiSIM? So this is what we need to do. In this exercise, we have these calculations to fill in. And so given this, given a 472 and this information here, I'm going to fill in my V peak in this particular case as being 10 V peak. I'm going to fill in my capacitor value as 4.7 nano farads. That's what we had calculated. So I'm going to take this and I'm going to highlight it. I'm going to take this and I'm going to highlight it. And then the calculated X sub C that we were able to derive for our exercise was 12.31 kilo ohms. 12.31 kilo ohms. So we'll go ahead and highlight that. So those would be the first three answers. We're going to calculate something here called impedance. And if you recall, you saw that briefly on our, not there, you saw that briefly Where did we see it? Was it in the form of, we saw it briefly here, impedance. Z, impedance measured in units of ohms, omega, and it was defined as the total opposition of current in an AC circuit. There are ohms that are exhibited by this capacitor, 12.31 ohms. There are ohms exhibited by this resistor, 6K ohms. What is the total ohms? Well, these ohms are calculated very, very specifically in a different fashion using this particular formula. For those of you who don't remember this formula is Pythagorean theorem. And Pythagorean theorem works this way. So let's go ahead and help you out with this here. Let's go and give you the short version, and then we'll give you the more detailed discussion in a little bit. So let me go off the share screen. I need some of these values though. So we happen to have a circuit, we happen to have a capacitor, we happen to have a resistor, and this guy is given as 6 kilo ohms. My X sub C is given as 12.31 kilo ohms, and my voltage is given as 7.07 VRMS, which is the same as a 10 volt peak. All right, that's good. So let's go ahead and do this. I'm going to unshare the screen and back on my worksheet. So you're going to see something very interesting here. I have these ohms, 12.31 K ohms, and these ohms, 6 K ohms, and I need total ohms because Z is equal to something called impedance, which is equal to total ohms in an AC circuit containing R with either cap or coil or both. So I have 6 K ohms, 12.31. Z is total ohms. What do you think? These ohms are in series. How do you find total ohms if they are in series? How did we find total ohms before? Z is going to be equal to my X sub C added to R. However, we can't add these two numbers directly with each other. These numbers are out of phase with each other. Why are they out of phase with each other? Do you remember our discussion with Eli the Iceman? With Eli the Iceman, we were able to demonstrate with Eli the Iceman that there was a phase difference between our X sub C and our, okay, that was demonstrated here. Let me go ahead and pull it out in a previous discussion. Remember we had this discussion a little while ago, and in this discussion, and there's a YouTube that I've chunked out for you all for this, for RC time constants. And when we have a capacitor and we have a resistor, the capacitor takes some time to reach full charge. The capacitor's current starts at maximum and it drops down to 0. And all this happens over how many time constants? It takes 5 time constants to reach a full charge. So that clearly shows that the current and the voltage are not in phase with each other. Current is at maximum before voltage reaches maximum. And the time frame between current and maximum, voltage at maximum, that time difference is called 5 time constants. The time constant, the individual interval, we were able to calculate tau was equal to R times C. Once we calculate tau, we multiply by 5, and the total time for this cap to reach full charge was whatever we calculated before. Knowing that the capacitor voltage doesn't happen right away, the summarization that we were able to make was a mnemonic. And the mnemonic that we used last time was right here, this is last week, was called Eli the Iceman. And the mnemonic is a memory tool. So in review of Ohm's law, the V and the E are synonymous with each other. And so anytime I see an E, it is equivalent to voltage. So for Eli specified in inductor circuits because the L stands for inductor, and C for ice, C stands for capacitor circuits. So if you look at this circuit, this ice, current is before voltage. So we say current leads voltage in capacitor circuits. Because there is this phase difference between voltage and current, we will see that phase difference realized when we do this analysis. So when we do this analysis, what happens here, my friends, is this. We will use my R value, that's my starting point, and I will draw a line, and I will call this R, and R is equal to 6 kilo ohms. At the end of the R, I'm going to draw another line, and this line, proportionally speaking, will be here, that's roughly 6, and roughly here is 12. So here is another line, and this is called X sub C. And X sub C is equal to 12.31 kilo ohms. There happens to be between these two arrows a 90-degree phase difference between these ohms. So these ohms would be 0 degrees, and these ohms here would be comma, negative 90 degrees. And so we will draw them coming down. And what happens here now is when we go to add these two, these are called phasors. Okay, so we have a phasor, which is a arrow with a length and direction. So the R phasor has a direction that's pointing to the right. It has some length. The X sub C phasor has a direction that's pointing down, and it has a length. I'm trying to draw these proportionally to each other. And if I go to do so, and I go to connect my beginning point to my end point right here, well, my result of adding these two guys together is now something called Z. Z is impedance. That's equal to Z. So I don't add 12.31 plus the 6, giving me 18.31K. I cannot add them straight up with each other. Why? Because they are out of phase with each other. They're 90 degrees out of phase with each other. I can, however, add them. I can add them. This adding is by using something called phasor addition. That's the method. The method is called phasor addition. And so I'm adding this phasor to this phasor, and I'm drawing them out this way, and I do a triangle between them. And so my total ohms is this part of the triangle. Well, guess what, my friends? If you don't recall Pythagorean theorem with right triangle math, welcome back to it. And there's a separate discussion which I'll offer regarding solving this using some basic trigonometry, but let's not even get into that word yet. Let's just look at this using Pythagorean theorem. So if you recall, if I have a triangle, a right triangle, here's a right triangle, and if I have a short side, and I'll call that A, and I have another longer side, I call that B, and the longest side of the right triangle is C, do you remember in Pythagorean, that's an A, theorem, in Pythagorean theorem, there's an E, I'm sorry, Pythagorean theorem, it's horrible. Pythagorean theorem, okay, that A squared plus B squared is equal to C squared. So who does not remember Pythagorean theorem explained back in middle school and high school math as being this? Hopefully you all remember it, or it's coming back to us. Now we have a practical application. Well, we know that this side squared plus this side squared is equal to this side squared. That's nice, but I'm looking for just C by itself. So how do I find C by itself? C by itself means I have to move the square from one side of the equation to the other side. Anytime we move a math function from one side of the equation to the other side, we rewrite that equation by using the opposite math function. The opposite of a square would be a square root. Then we put in our A squared plus B squared, and that's equal to C itself. Or if I write it the way equations are usually written, I will start with C, and C is equal to square root of A squared plus B squared. And does that look a lot like my formula that was shown on the previous page for Z? Z is equal to the square root of a value of R squared, because that's one of the sides of a right triangle, and I'm going to add that to the square of the other length of the triangle squared. So I have R squared plus X sub C squared. This squared plus this squared must equal to impedance squared, or impedance is simply square root of this. So if I pop this into my calculator, I should have this written out. I should have 6k squared plus 12.31k squared. And the way that, and you'll have to find the method that works for your calculator, but let me go ahead and write out what I would approximate as a keystroke sequence. Let's try this out. Keystroke sequence. So for some of you, it would be a square root at the end. For some of you, it would be square root at the beginning. It depends on your calculator. I'm going to use this. I'm going to start off with the square root key. And then I'm going to insert an open parentheses. And then I'm going to put in 6 exponent 3, and I'm going to hit x squared. This is a square function now. And then I'm going to hit a plus 12.31 exponent 3. And I'm going to hit a square here also. This is a square, not reciprocal, my friends. And then I'm going to hit a close parentheses. And then finally, I'm going to hit a equals. So that should be a universal pathway to successfully calculating my impedance for this particular circuit. And why don't all of you try this as I turn on my calculator, clear it, and I will do the same. So my square root key is a second function. I've engaged my square root. I'm going to engage in open parentheses, engage 6 exponent 3, but I have to square it. So here's my square key. Then I am going to hit add, and then I will have a 12.31 exponent 3, and I have to square it as well. Hit close parentheses, and then I will hit equals. So that number should be something larger than 12.31. I get 13.69 k ohms. Could you try that sequence and see if you're comfortable with your result, which should be hopefully close to what it is I have on my calculator. This keystroke sequence, 13.69 k ohms. So this gives me 13.69 kilo ohms, and this would be equal to Z. And how is that significant for us? Is if you're able to get those ohms, that is the total ohms for the circuit. So my Z up here, I can now write down Z is equal to 13.69 kilo ohms. Once I have this, can I calculate, please, the amount of current that flows in this circuit? I sure can. I have a 10-volt peak. I have this amount of ohms. I should be able to calculate my peak current here. Let's see if that's what I want on my sheet. Let me come down here. Peak, 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 peak. Okay, yeah, everything's in peak. That's fine. So double check first that you're comfortable with this calculation for impedance. Does anybody have any questions regarding this aspect on your calculators? Christian, are you able to get this number? You feel comfortable with this? Rolando, Pauline, Wenbin, Andrew?
Yeah, I got it.
Okay, Christian's good. Rolando, you okay with this calculation? You worked it out? I didn't see that display for a moment, but yeah, good job, Rolando. And Christian, good job there. Pauline, are you okay with this? Did it work out on your,
Yes.
and Andrew and Kyle?
Yeah, mine worked really good. Thank you.
And now, okay.
Good, okay.
Yes, it
All
worked
right.
for us.
All right, so that's your total ohms. I now want I total. How much electricity is flowing in this particular circuit? Now, the direction of current alternates. Part of the time it's going clockwise, part of the time it's going counterclockwise. So the direction of current in this case is not as important as the amount. So if I take my 10 volts peak and I divide by this, so take 10 and divide by your 1369 k ohms, and now generate a current, and it will be a peak current. Some amps or milliamps or microamps, whatever it works out to be, but it will be a peak current because I'm using 10 volts peak. So please do that calculation. Take 10 volts peak and divide by your 13.69 kilo. And Andrew, do you have a current for me, please?
No, I'm still working on it right now.
10 divided by 13.69 kilo. Pauline, do you have a number for me?
I'm getting 730.46 microamp.
Okay, so with memory, you should have something very close to 730.23 microamps. And like I say, if you're a few hundredths off from my calculation, that's okay. I'm using as much memory as I can. Okay, and that's peak. You got to add a little peak at the end. So far, so good. Is everybody able to get that number or something very close to it? Now, can we calculate the voltages on each of these guys? What is going to be my VC? What is going to be my V over the resistor? How do I calculate V? According to Ohm's law, don't forget, right over here, my V is equal to I, and then I will put down the omega symbol instead of R. Instead of an R, I put down the omega symbol because ohms applies to X sub C and to Z. So if I want V, it's simply current times those ohms. Do I have a current going through the capacitor of 730.23 microamps peak? Done. Do I have ohms of that capacitor? Yes. So if I take this current, 730.23 microamps peak, multiply by these ohms, can I calculate a peak voltage on that capacitor? Let's go ahead and do that. Take the current, enter, times these ohms, and I happen to have a peak voltage on the capacitor. Volts peak. All right. And Christian, what is it that you calculate?
I haven't done it yet. Sorry, I was grabbing.
Okay, yeah, it's a lot of pieces. 730.23 microamps, so exponent -6 times the 12.31 exponent 3 will give you this voltage that we're looking for.
I got 8.98 kilovolts.
Is it kilo?
Well, I got a 3 at the end of my exponent unless I typed something wrong.
I think you did because this is micro. This is
okay, yeah.
-6 here, okay, not -3. So watch this very carefully. Rolando, do you have a value?
I got 8.98 volts then.
Okay, so it works out to be 8 point, and if I use all the memory, 8.99 volts peak. Okay, okay. Now, something very close to it. You could be within a few hundredths. Now, how about the voltage for the resistor? I simply take the same current and multiply by 6K ohms. So let's go ahead, take that current of 730 microamps and multiply that by 6K. And what is it that you calculate? Now, question goes to Kyle. Might you have a value for us here? 730.23 micro times 6 kilo ohms. What do you have?
1 second. I'm doing it right now.
Okay.
That is, I got 4.38. What would be the 4.38?
This is a VR, so my units are going to be volt
VP. Okay.
volts peak. Okay. All right. Very good. So you look at this, you should have something very close to 4.38 volts peak. So you look at this, Andrew, take off your mic. All right. So you look at this, you say, well, I have a series circuit. And in this series circuit, I have these ohms in series with these ohms. I can't add them straight up with each other. The 12.31 can't be added with 6K to give me 18 kilo ohms. Why can't I add them straight up with each other? Because they're out of phase with each other. Now you look at the total volts. Watch this for a moment. You got 8.99 volts here for this capacitor, You got 4.38 volts peak across this resistor. How does adding this plus this possibly going to give you 10 volts peak? Did something go wrong with my math? Absolutely not. You are on track. Because remember, the same way we can't add these ohms together because they're out of phase is also the same reason why you can't add these voltages together because they're out of phase with each other. Oh, very interesting. So let me offer you this thought. This thought is I'm going to use this triangle that we drew in earlier, and I have a, this will be my R phasor is here. So this will be my VR, and this is equal to 4.38 volts peak. This will be equal to my VC of 8.99 volts peak. So what I'm looking for my hypotenuse will be V total. This is interesting. I'm adding this number to this number, but I can't add them straight up with each other because they're not in phase. I have to use Pythagorean theorem. So I'm going to use this formula again. I'm going to use the C, that long hypotenuse is equal to the square root of the sum of these two numbers. Isn't that interesting? Let's see how that works out for us. I'm going to put this in here this way. Let's go ahead. My V total is going to be equal to the square root of 4.38 squared plus 8.99 squared. The whole thing is underneath the square root symbol. And if I were to offer that as a keystroke sequence, I would write it for you this way. I would offer that as a square root function first, square root, open parentheses, then 4.38 squared, then plus 12.31. No, sorry. My eyes are going in two different directions. I apologize. Okay. That would be 8.99 squared, and then followed by close parentheses, and followed by equals. So if I use this keystroke sequence in black, and I'll do this right along with you, I'm going to clear, open my square root function, bring in an open parentheses, 4.38 squared, I'm not going to use memory in this case, plus 8.99 squared, close parentheses, and I'm going to hit equals. What do I end up with for voltage total in this triangle when I add these two phasors together? What do you end up with?
10 volts.
Wow. Hopefully you end up with a nice 10 volt peak. This is equal to 10 V peak. Isn't that cool? There's one more calculation, and that one more calculation is something called phase angle. And the phase angle has to do with, watch this very carefully, from my horizontal phasor to where the hypotenuse ends up. There is an angle that comes from here going downwards because this triangle is drawn this way. What is that phase angle? And the symbol for the phase angle is shown, it looks like an oval with a horizontal line through it. That is called, there's a Greek letter, that is called theta, okay? So I am looking for the angle of theta. It's drawn that way. I'm looking for that angle of theta, and the angle of theta has a very simple, but it is a very specific calculation. I'll give you that formula in just one moment. But before I go to play with theta, are you okay with these issues we've discussed so far? The first time you've been introduced to phasors, and we draw phasors because in a capacitor with a resistor circuit, these quantities are out of phase with each other. Why are they out of phase with each other? They're out of phase with each other because of our friend, Eli the Iceman. How does Eli the Iceman come about? Because of our discussion of RC time constants. And in RC time constants, we know that current will lead voltage, and it leads voltage by 90 degrees. So they are clearly out of phase with each other. So we reconcile that on our current worksheet by drawing phasors that are 90 degrees out of phase with each other. The R phasor, 6 k ohms, the X sub C phasor, which we calculated 12.31, and we draw them roughly to scale. We see something like this. Our total ohms is called impedance, drawn by the horizontal. We use Pythagorean theorem to solve for the hypotenuse. C is equal to the square root of A squared plus B squared. However, using the specific lettering that we had here, the hypotenuse is replaced by Z for impedance, and the A squared B squared is replaced by R squared plus X of C squared. Pop in all these numbers, we end up with an impedance of 13.69 kilo ohms. That is the total ohms for this circuit, 13.69 kilo ohms. From here, we need to determine a total current. So 10 volt peak, divide by this, according to Ohm's law, will give us a peak current of 730.23 microamps peak. That is the current that flows through the cap. That is the current that flows through the resistor. Knowing the current and the ohms, according to Ohm's law, again, we can calculate the voltage. We calculated a voltage for the capacitor as 8.99 volts peak. We calculated the voltage on the resistor as 4.38 volts peak. And by popping these two numbers into a separate phasor diagram, our phasor is always on top, pointing at 0 degrees. The X sub C phasor is always pointing down. The vertical phasor, we pop in those values. We're now solving for total voltage. And we solve for total voltage only to prove to ourselves that this number is good when we add it to this number. Now remember, we are not adding directly. We're not going to get 12, 13 volts by adding these numbers directly. Why can't we add them directly? Because they are not in phase. So we have to use our friend Pythagorean theorem. So to calculate this voltage, we're going to use Pythagorean theorem. The C is equal square root of A squared plus B squared. We're going to translate that for voltage. So V total is equal to the 4.38 squared plus the 8.99 squared. And lo and behold, you end up with something that is pretty darn close to. In fact, my calculator shows 10.000225. Is that pretty darn close to 10 volt peak? Yeah. And so let's go ahead and write this here. 10.000225 volts peak. So that means our numbers are good. All right. So the last thing to calculate mathematically is this thing called theta. And theta has a very simple formula, which I'll give to you here. So angle theta for the exercise that we have right here. So my R value was 6 k ohms. My X sub C value was 13, scratch that. Let's do another sheet. All right. R is equal to 6 kilo ohms. X sub C we calculated as 12.31 k ohms. We were able to successfully determine a total ohms, which we will draw in using a diagonal, and that was called Z. we are now looking for this angle in here called theta. So angle of theta is equal to inverse tangent of x sub c over r. Okay. And on your calculator, you would probably hit, many calculators to hit the inverse function is probably a second, and then tan, and then 12.31 over 6. The kilos don't matter because they'll cancel, and then hit equals. It's a relatively simple calculation as calculations go. Let's go ahead and try that on your calculators. So find the tangent. So in this particular calculator, the tangent function is shown here. My inverse tangent function is shown as an second function in blue. So I have to engage second tan, and now it shows up as tan negative 1, which is an inverse function, and it generates an open parentheses. I will then pop in, sit over adjacent, I will then pop in 12.31 and divide by 6, close parentheses, and hit equals, and be done with it. When you go to do so, what answer does your calculator show you? So the question goes to angle theta. Rolando, what does that show you? You're doing second tangent, inverse tangent, 12.31 divided by 6 equals. That's all there is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 keystrokes. And are you doing inverse tan with a inverse tan? Yeah, if your calculator doesn't automatically generate the open parentheses, you will need to generate the open parentheses. So your keystroke sequence, let me modify this for your calculators, because mine generates an open parentheses. Let's do, this is equal to second tan, that'll give you the inverse tan function, and then hit open parentheses, 12.31 by 6, and then close parentheses, then hit equals. So in your calculators, you may have to insist on putting in the open and close parentheses. So when you go to do so, hallelujah, isn't that marvelous? You should end up with, yes, that looks really good, Rolando. Christian, do you have a number for us?
64.01 degrees.
It works out to be 64.01 degrees because the angle is always measured in degrees. Pauline, Andrew, and Kyle, are you able to get this calculation?
Yes, actually, after much experiment in trying to get it, it's actually
Yeah.
64.
And that's what is going to occur in this particular case, because all your calculators are slightly different. But that's all right, as long as you find the method that works, because this is the number we're supposed to end up with.
Yeah, so I had to do the tangent at the end. I didn't have to do the parentheses. I don't know if other people have the same thing, but
I don't have to do the parentheses either, because my calculator automatically generates that open parentheses. So anytime I hit inverse tan, that open parentheses is automatically generated, and then I just type in what I type in. So my 12.31, and then divide by 6. I don't even have to hit close parentheses on this calculator. I can just hit enter, and it'll close the parentheses for me, and I'll end up with the same number of degrees. So each calculator is slightly different, and for some of those that do not automatically generate the open parentheses or close it, if you use the second keystroke sequence, it should get you to the promised land. and reflect 64.01 degrees. Are we good with this so far? Now, let's take all this information that we recently calculated and go back to my share screen. And so back to my share screen, we can now pop in some information here. So for impedance, we can now pop in a value for impedance. And the impedance we were able to determine was 13.69 K ohms. That's my impedance. So far, so good. Yay. And we were also able to determine a current. And the current we were able to determine was 730.23 microamps peak. Oops, I didn't type in something, sorry. 730, so 730.23 microamps peak. So in filling this guy in, I fill that in yellow, go ahead and do this guy also in yellow, boom, take away some of that spacing. Now I also was able to calculate a voltage peak on the resistor, and the voltage peak on the resistor was calculated as 4.38 V peak. That's a decimal point, sorry. So put in a decimal point and highlight that puppy. And I was able to calculate a voltage peak on the capacitor of 8.99 V peak. And so there's my voltage peak on the capacitor, highlight that. And we were able to calculate a phase angle of 64.01 degrees. Okay, as my phase angle of theta. So that's what we were able to accomplish so far. Now what we're going to do is we're going to check out what was measured on the oscilloscope. What was measured on the oscilloscope here in MultiSIM is our voltage on the resistor. And we discovered that the voltage on the resistor was on channel B. Channel B shows a positive lead over here, coming up to the top of the resistor. And that showed on the lower waveform as something less than 5 volts. It may be a little hard to read here. I'm going to change the scale of these guys. I'm going to change the scale of channel B so that I can magnify this. It's a little taller. I'm going to change the scale on this guy so it's out of the way for channel A. So channel B at 2 volts per division is now more clear. And if I look at this and I move this cursor over to my middle line, gently, if I can move it to the middle line somewhere, any kind of grid that I can achieve. Okay, each square for channel B is 2 volts. So if I start here and I count up 1 division, 2 division, and it looks like it could be a 0.2. A 2.2 is a good approximation from here to this peak. Does everybody concur? I have 2 divisions plus a little extra. I'm just going to call that out as 2.2. If I call that out as 2.2 divisions times 2 volts, what is my volt peak on that resistor measured wise on the oscilloscope? Doesn't that come out to be a 4.4? And if you look at this, this one actually tells me on channel B what my peak is, 4.39. That's even more accurate than my approximation. So let's go with that because that's measured on the oscilloscope, 4.369. Does everybody see that number right here on the MultiSIM? Give me a yes or no.
Yes.
Okay, so 4.369. 4.369 capital V. Oh, And how does that compare to my calculated right over here? Are they reasonably close to each other? I got 4.38 volts peak, and over here I got 4.369 volt peak. Pretty darn close. All right, that's real world. We won't talk about measuring this voltage on the capacitor right now. We're going to talk about measuring the phase angle. And so how do we do that? This is very simply done by following these steps. So what we want here in this step is the number of divisions between the two cursors of my display screen. So the number of divisions between the two cursors. So I'm going to have to move my cursors. I want one cursor. I'm going to grab this cursor. I'm going to try to grab this cursor. Go on, be nice to me. All right. And I'm going to pick a nice crossover point here where this goes from, this one goes from positive to negative, and the blue one, bring this guy over, grab it carefully. And this, where this other waveform goes from positive to negative. So I now have the crossover point. These are called crossover points, where one waveform crosses over the zero line, the other waveform crosses over the zero line. And the best that I can approximate this right now, what is shown as my difference of time between these two? 72.491 microseconds. Does everybody see that? Let me adjust this. This is not, I'm going to bring this guy back. Yeah, I need a better crossover point. Right to here, that's a better crossover point. And if I magnify this, this is pretty good. I have a good 0 point here and I have a good 0 point here. So my time difference looks like 63.197. I'm going to pop that in here. Oh, number of divisions. Period of time between the two cursors. Period. The time between the two cursors. Number of divisions between the two. Degrees shift. I think I'm going to want to rephrase this, but here we go. I'm going to put in this number 63.197. 63.197 microseconds. I'm going to highlight that. And what I'm going to do here is, instead of number of divisions, I'm just going to rephrase this to time. Time between the two cursors. Now the period has to do with the time for one complete cycle. Okay, period of time, and I'll put down for one cycle, time of one cycle. That's how we defined period the last time we looked at this. And the period for the entire waveform is, I will go ahead and select this guy and move it over to here. So if I look at the large waveform, does my large waveform cross over the zero line at the red cursor from the positive half cycle to the negative half cycle? And then it goes through its rotation. And does my large waveform again over here cross over from the positive half cycle to the negative half cycle? And the answer here is yes. So my large or my smaller waveform here, let's just use the larger waveform right here and grab this guy right here. Okay, is that the time for one cycle? Do you all feel comfortable and happy with that? Or some of you might prefer the starting point of a waveform. Let's go here, and then where the waveform starts to repeat itself. Maybe that's a little more uniform with the discussions we've had in the past. So take a look at the larger waveform. This is where it starts from the zero line, goes positive, goes to here, switches over to the negative, it comes back over, and this is where it starts to repeat itself. Are we in agreement that I have one cycle between these two cursors? Done. What is my time between these two cursors? T2 minus T1 is 364.312. 364. 364.312 microseconds. That's a decimal point, not a comma, sorry. All right. Now, what is my degree shift between these two? The degree shift between these two will be the time between the waveforms divided by the period. In other words, this number divided by this number. So this will be equal to the 360. Now these are both in microseconds. So the microseconds will cancel. So let me just fill this in for you. This will be 63.197 divided by 364.342. And then we're going to multiply by, that's my multiply by 360. Because I have 360 degrees here. So I am following this formula here, that this is the time between the waveforms divided by the period, multiplied by 360 degrees. So do this math. There's nothing complicated about this math. Could you take 63.197 and divide by 364.342 and then multiply by 360? I will go ahead and do that, and I will call out for a calculation. Times 360. And calculation from Andrew, do you have this calculation? Kyle, do you
No,
have
I'm
this?
working on it.
You punch in what I've highlighted in yellow, these numbers right here. I called them out. The 63.197 divided by 364.342 times 360. So you should be able to punch it as I've read it 3 times. So Kyle, what number do you have?
62.44.
62.44. Uh-huh. And Andrew, what do you get? Pauline, what do
I
you
got
get?
something different. I got 173.45.
No. Do this math exactly as you see it. Kyle was correct. Pauline, what do you get?
I got 62.44 degrees.
62.44 degrees is what we calculated, okay? And highlight that in yellow. The question here is, does this compare reasonably to your calculated phase angle up here? I'll do this in a slightly different color, okay? Do these 2 degrees calculate reasonably close to each other? You're calculated using Pythagorean theorem was 64.01 degrees, and best as we could determine from the oscope, 62.44. That's really, really good. So the answer here would be a resounding YES. Okay, keep in mind, it's not going to be exactly, it's going to be these words, reasonably close. Okay, and it is reasonably close. Why is it going to be reasonably close? Because your waveforms here, remember where we move the cursors, we're all by eyeball. best as we could approximate these positions. And these numbers are very, very, very good. So we can finally put up here for measured phase angle 62.44 degrees for the measured phase angle based on our oscope. Okay, we couldn't do that until we did this math over here. Whew. Okay, that is your quick introduction to something called phase shift. And it's called phase shift because the peaks are not aligned. The crossover points crossing the zero line are not in sync with each other. It's okay that they're different heights because they're different parts of the circuit, but they're not in sync with each other. One is clearly in front of the other, one is clearly behind the other. So the words that we use are that they are out of phase. How many degrees out of phase with each other was dependent upon how we played with our cursors in order to determine these. The least and the value we don't need this one here. In fact, I'm going to eliminate it because in order for us to actually measure it, we have to do other things. I'm just going to take that out completely because that's not critical for us at this point. But everything else with the modifications that I've adjusted for this particular circuit will hold. And I will save the circuit and I will attach the circuit to a page in Canvas so that you can have the entire page to work with. You will have the blank version of this. You will also have the filled in version of this, and you will also have a nice screenshot of this particular MultiSIM. And then all of this is, of course, recorded in Zoom. So that being said, my friends, we went through a lot. And I commend you for hanging tough with us. So you have a number of things to do. Most of you did very well on the superposition, so you will have another superposition exercise to play with. You already know in Canvas that you have your videos that you have to view. You have some homework questions that you have to answer. And then there will be a MultiSIM exercise for you to do in MultiSIM. So you've got a pretty full week ahead of you for things to do between now and when we meet next week. Don't hesitate to ask questions along the way as questions arise. I'm very approachable and by Canvas email. So hit me with those questions as they arise and I will go ahead and get you going. I have another Zoom meeting I am behind on attending, so I need to attend to that. So any questions that you have, please let me know by Canvas email, okay? Any quick questions before I sign off? Okay, so if there are no quick questions before I sign off, follow-up questions, then by all means, ask me by Canvas email and we'll attend to those. So with that, thank you very much for a most wonderful day. Get your screens back on here, gallery view, so I can take a picture of you all, smiling faces for the dean, and I will get going with my other meeting in just a moment. It's okay to go a little bit more for you guys. You guys are worth it. I'll be tardy. I'm going to be tardy. Oh, God. Dean's going to kick my butt. Okay, 1, 2, and smile. Okay. Okay, got you guys. All right, have a lovely week. All right. And study hard. Take care. Adios.